All right, so this is a tutorial on how to use GPRray and GPRray inv. GPRray is available on GitHub, Parsekian/GPRray, and you can download the most current version of that script. So I'm just going to go through a few simple things that you can do with the script, and the expectation is that you will you go in and revise the script however you want to have the functionality that you need. So I assume that when you're starting this that you've already downloaded some basic parts of the code. The minimum that you need in order to start here is just the GPRray.m, which is freely available. I'm working on getting GPRray inv.m available, and the dependent of that is dixcalc. You do need that in order for GPRray inv to work. So besides that, for simplicity, I'm just assuming that you're running all of these in the same folder. I have a couple other things in this folder that you probably won't have, but yeah, the key ones to have are GPRray, GPRray inv, and dixcalc. I've opened up GPRray here and GPRray inv, just because those are the ones that we're going to likely look a little bit more into what's going on in the code. So the very first thing that you might want to do is just forward model some travel times for multi-offset GPR. And so this function is just set up so that if you the result will be stored in a TT parameter, and you can name that whatever you want, of course. The function is just GPRray, and then in the X vector, and this is all defined down here, you need to define your receiver locations. Now the forward model will always use the same receiver locations for all offsets. The inverse model is not required. You can use field data, and then that would it might not have exactly the same offsets picked for each layer, for each reflector. The next parameter you have to put in is v. So this is the velocity for each layer, and you don't need to explicitly say the number of layers, just however many velocities you put in is going to be the number of layers that you're simulating. And then similarly, z must be a vector the same length as v, and this is the thickness of each layer. The only real limits here for velocity are physical constraints. So between the speed of light in a vacuum, 0.2998 meters per nanosecond, and the speed of light in water, or something around 0.033 meters per nanosecond. In terms of thickness of the layers, yeah, again, not really any true constraints, but reasonably, we're not simulating hundreds of meters here, just because most GPR measurements are not going to be able to detect hundreds of meters below the surface. Your plot on flag is going to be set to 1 at most times. It just shows the plots, and it actually changes the output slightly. It sets it in a matrix instead of the cell array, and we'll see that again later. But I would just encourage you to keep the plot on flag at 1 at all times. The current version, as of February 2019, that's on GitHub, includes a noise component, and this is nothing fancy. It's just a little bit of, a simple way to add a little bit of noise just to be able to play with how noise affects the inverted result. And so everything is commented here fairly concisely, and so the way that I would suggest to run this function would just basically be like this. So it doesn't need to have brackets, and then we'll just say so 0.1 by 0.5 to 5, let's say, and then we'll just do 3 velocities. So anything physical, 0.12, 0.1, 0.08 would all be fine physical velocities to use. And then we can use some reasonable depths. And then we'll stick a thin layer in here. So we have one layer that's 2 meters thick, one layer that's 3/10 of a meter thick and another layer that's 3 meters thick. So this middle one is going to be a thin layer. Plot on, as I said, it's probably, for the most part, you just run it with the figure on. It doesn't really take much longer to calculate, so there's no real reason to turn it off. And to start off with, we'll just have no noise. And so if we run this, then we will get two figures. So figure 1 shows the ray paths, and just kind of helpful to see the geometry, for your own whatever value you may get out of that. And then maybe the one that's slightly more valuable is seeing the reflection hyperbolas in offset versus time space. And then you can see the result of that is a new parameter here in the workspace, TT, and you can see this is a cell array. And if we go ahead and open that up, then you see that you get a cell array. And so there's a number of cells equal to the number of layers that you defined. And each cell has in it, the top row is offset in meters, and the bottom row is nanoseconds, the travel time. And so that's the same type of syntax for all, or same type of format for all of them. And the reason it's stored in a cell array, again, is just because if you have a different number of offsets, commonly like you would encounter with field data, where you might not be able to pick every single trace for every single reflector, then you can't store that in a matrix. So I've just stored it in a cell array because a cell array can handle all any different length of vectors for each different layer. So that's simulating the data. This is the forward model. It runs really fast. Obviously, if you add more layers, it does take a little bit longer because there's an optimization problem just to figure out how to set up the angles for the first layer. But realistically, no realistic number of layers is going to take a particularly long time. So besides that, you can review what the code does yourself. We have our functions are embedded, so you only need the one file, but there are subroutines here. So example, n-layer arrays is something that is a nested function at the bottom. And so there are, if you found value in just parts of the code, there's certainly things that you can extract and they'll work on their own. So that is pretty much how to execute that function. So once you have some data, some simulated data, the next useful thing to do would be to invert that simulated data. And yeah, for most people, the objective ultimately will be to invert some field data, but it's of course great to practice with inverting the simulated data. So here we can go over to the GPRray inv component, and so what we have here is this function where D is the result D is going to be the inverted data, the inverted results. The fit parameter, so the goodness of fit, the res norm parameter, and the residual are also going to be produced if you want them. You can, of course, choose not to get those if you don't want to. The input, you need data. And so the data in this case takes exactly the same form as that TT that we just simulated. So the result from GPRray is just exactly the right format to go into GPRray inv. So it's really easy to do these sort of like testing experiments. The other thing you need is a starting model. So I'll actually just put TT in here because that's what we're going to do first. The next thing you need is a starting model. And if you just leave the starting model as 0, then the inversion is actually just going to use the Dix calculation as your starting model. And that's actually fine. Dix tends to get you pretty close to the right answer. It just fails miserably if you violate some of the assumptions. So yeah, it kind of works if you, for most cases. The caveat there is that there are cases where Dix will not calculate under certain velocity structures. So if that's the case, it will just automatically revert to uniform velocity. And it really doesn't seem to make all that much of a difference. But yeah, prove me wrong if you think that's an incorrect statement. So usually just leaving the starting model at 0 is fine for inverting most data. But of course, for testing, it's great to test out different starting models. The convergence criteria is, it's basically fine to just keep it as a small number. This is the optimization engine here is LSQ nonlin, which seems to be pretty stable and pretty robust. So you shouldn't need to worry about that convergence criteria all that much. And this is the objective fit the convergence criteria. And what I find is that normally the solution converges because it's not getting any closer. It's not moving any closer to this minimum. So realistically, as long as you choose a small number here, it doesn't really matter. But again, you might find in your testing that it makes more of a difference. Please let me know. So yeah, then just to execute this, I would run it right from the command window. And so I'll just sort of slow down here and look at what happened. Right. So here, so we executed the inversion right here. And then what it's going to do is it's going to iterate through, and I think every 10th iteration, it's going to display its progress. So the first column is the residual at that iteration. And then the next 3 columns are the 3 velocities, and then the final 3 columns are the 3 thicknesses. So if you have more than 3 velocities, then it will be n number, the first n number, and then the second n number of columns will be the thicknesses. Now you're immediately going to notice that these velocities are non-physical, even though this is an inversion in progress. You would expect the velocities to be closer to physical than this. And the reason for that is that just because to get LSQ nonlin to work very well, you need to have all of the numbers in the same order of magnitude. So all I've done is just to get it to work just to get the inversion to be happy, I've multiplied the velocities by 10. And then when it comes to actually producing the results, it's going to then automatically divide them by 10. So you get velocities in the correct units. So this is the inversion progress. And it says, okay, I found a minimum. And then it gives you D, the results. And so the result here says the velocity of, not 1.19. It says, it's 0.12, which is a physical velocity. And the second layer velocity is 0.1, third layer velocity is 0.08. And as you will recall from our input values were 0.12, 0.1, 0.08. So it recovered those perfectly. And then our thicknesses was supposed to be 2, 0.3, and 3. And you can see that the thicknesses that we recovered are 1.99 and 0.3 and 2.99. So again, we recovered our thicknesses and velocities virtually perfectly. Not surprising considering we didn't include any noise on that data. And so, I actually forgot to terminate that with the semicolons. So we ended up with actually plotting out the residual. And so this is the residual for all 30 of the data points we were simulating. So that is how you execute the inversion. So the next thing to do, just a simple experiment that can be good to play around with, would be to come back up to our forward model, right? And this time we want to add some noise. And so the one note about the forward model is that if you put noise on it, you'll get this figure, right? And this is the same type of figure we were looking at before. This figure doesn't actually display the noise. This shows your perfect travel time curves, but it doesn't account for the fact that you've imposed noise on it. However, it is the noise that you imposed is included in that travel time, in that TT cell array over here. So when we go to our inversion, So here we're using exactly the same input parameters as we did last time, except in this case we're going to have a noise at 0.5. So when we go to our inversion this time, so now we see the progress, and we get a different result. So what we get from the result of the inversion this time, we get here is the progress towards fitting, and so the starting model got us right here, and we ended up a little bit in better shape after 35 iterations. And here you can see the simulated data found by the inversion is in red, and our forward model data that we have added noise to is the black. So you can see that the actual noise is represented in the data in the black. So that's like a relatively low noise data set. Yeah, it had no problem fitting it whatsoever. And you can see that if we go and show what the result is, it found the first layer velocity to be 0.119, so really close to 0.12. The second layer velocity didn't get all that well. So this is supposed to be 0.1 and it got 0.08. And the third layer velocity, it got at 0.75. It was supposed to be 0.8. Similarly, yeah, it did a pretty good job getting the first thickness, and the second thickness was off by a little bit, which isn't too surprising because it didn't get the velocity quite perfectly. And then, of course, the third layer thickness was again quite close. But it just shows you the ability of the inversion to resolve the parameters under different levels of noise. And that can be a really good sort of, it can be really informative for how accurate you think your interpretation of field data could be. If you can estimate your errors, your picking errors on your field data, and then you can use that information to forward model some different scenarios. So we can just, I'll just do one more here where I will make it really noisy. And then, right. Yeah, it's interesting. So in this case, we started out and then it got much worse, but eventually it sort of came and settled down at a reasonable minimum. And you can see that this was quite a bit noisier, and realistically, this is probably noisier than your pics would be in reality. But it certainly found answers that are, at least based on a visual inspection of the result, the answers aren't too bad. So let's go and see how it did. So our input was, input was the same thing. So we were looking for 0.12, 0.1, and 0.8. And we didn't do too great with the middle layer, but we did pretty well with the other two layers. And again, the thickness is not too bad. Overestimated that one a bit and overestimated that one a bit. But that's kind of what you would expect in this case, where we have a thin layer and in the middle of it. So if you use, we can do another quick one where we'll simulate something with no thin layer. We'll just say these are all going to be 2 meters. And then we'll also give it more offsets. Okay, so, and this is still a very realistic acquisition scheme, right? I mean, to have 10 meters of offsets in a field data set would be totally realistic. So that's what our simulated data looks like. Still have the same level of noise on it. And then here I'm just going to run the inversion again. It's going to take a little bit longer this time, just of course, because it has more data to simulate. Right, so here again, you can see the data is relatively noisy, but inversion has no problem coming up with some kind of reasonable guess at it, and a nice convergence curve there. Let's see how it did. So we are looking for 0.12, 0.1, and 0.08. So we did really well on that because we don't have a thin layer this time. So even though there's not a lot of noise, so even though there is a lot of noise, because we don't have a thin layer, we're able to recover our velocities really pretty accurately. And then our thicknesses, they were supposed to be all 2.0, and they're all very close to that. So it gives you a sense for where your performance can be challenged and where you have a good ability to recover your velocity structure even if the data is noisy. So the next functionality that would be good to add to this is the ability to easily import pics from field data. And you could see how it would be, you could see how you could script that yourself without too much trouble. All you have to do is end up with your pics in this type of travel time array. So each layer has a different cell, and then each cell has travel times and offsets. And of course, the inversion is happy to take different lengths in that TT cell array. I'll probably work on that, hopefully soon, but no promises. If you find yourself interested to work on that, you should go onto GitHub and grab the code and upload your version as a branch.